Hi everyone, and welcome to our course on statistical methods in high-energy physics. As you know, high-energy physics is not about production of huge amounts of energy in nuclear power plants or in explosions of atomic bombs. It's much more about careful analysis of huge bursts of data. High-energy physics is studying the smallest known particles that are often very rare and difficult to produce. It also studies very rare or hypothetical behavior of well-known particles. And, of course, it studies well-known behavior of well-known particles, but with a new precision. For all these purposes, a huge amount of data is needed. Unfortunately, data doesn't speak for itself. Drawing conclusions from data can be a very tricky task, and the analyst must be very careful if he or she doesn't want to misinterpret the data. In this course, we would like to guide you through the main concepts of statistical evaluation of data that are used in particle physics. The course is split into four main parts: parameter estimation, hypothesis testing, multivariate analysis techniques, and data unfolding. All this will be preceded by a short introduction to the concept of probability, basic terminology, and mathematical tools used throughout the whole course. In parallel, we prepared example computer programs that use statistical software tools common in particle physics community, and we invite you to run these programs, look at the source code, get familiar with it, and try to adapt it in your own needs. After each part of the course, you will get the homework based on these programs. Let's start with the mathematical definition of probability. You will see it's very simple and, as often in mathematics, it doesn't tell much. Later, you will learn that there are two ways how to use this abstract concept in practical situations and defining the meaning of probability. So let's start with the mathematical definition. Let U be a set of all possible events, so-called sample space. Let A be an event or a set of events from this sample space. A is subset of U. Then the probability P of A is a number obeying the following three conditions that are known as Kolmogorov axioms. Probability of A must be greater or equal to 0. Probability of U must be equal to 1. Probability of A or B is equal to probability of A plus probability of B for any A and B which are exclusive, meaning that intersection of A and B is 0. And that's it. All properties of the probability theory can be derived from these three axioms. Here are some implications of the axioms. Probability of A not happening is equal to 1 minus probability of A. Probability of A or A not happening equals to 1. Probability of no event happening is equal to 0. If A is subset of B, then probability of A must be less or equal than probability of B. And finally, probability of A or B is equal to probability of A plus probability of B minus probability of A and B happening at the same time. Very often, you will need to work with probability that some event A happens, given that you know that also an event B happened. This is called conditional probability, because there's this condition on B. We denote it as probability of A given B. It is interesting and important to realize how to calculate the probability that A and B happen simultaneously with the use of the conditional probability. Probability of A and B equals to probability of A given B times probability of B. It is quite obvious that it can also be expressed as probability of A and B equals to probability of B given A times probability of A. The unconditional probability of B to happen can be expressed as probability of B equals to probability of B given A times probability of A plus probability of B given not A times probability of not A. We have just defined the probability in a mathematical way and studied some of its basic properties. Until now, probability was just an abstract mathematical concept. We haven't specified what the sample space U was and what were its elements A, B, and so on. Also, we haven't assigned any concrete meaning to the probability P of A. There are two basic ways how to do it, and let's pick the so-called frequentist approach first. This approach states that elements of the sample space are possible outcomes of a repeatable experiment. If you repeat the experiment infinite number of times, then probability of A is the relative frequency of the outcome A. Hence the name frequentist of this approach. In other words, if n is the number of repetitions of an experiment, then probability of A is the limit of the ratio of the number of times the experiments resulted in A with respect to the number of experiment repetitions. Probability of A equals to limit of n of A over n, where n goes to infinity. Note that the frequentist probability is not an intrinsic property of the event A. It depends on the chosen ensemble. For example, probability of person dying before 40 is different for ensemble of all humans, all male lion tamers, and so on. Also note a shortcoming of the definition. Probability of A is quite hard to determine for unique events, like the Big Bang. We've just seen that the frequentist probability is defined in a mathematically rigorous way as a relative frequency or occurrence of the result A and the limit of large number of experiment repetitions. In comparison, the Bayesian approach to the probability might sound a bit strange at first. Within this approach, elements of the sample space are hypotheses that can be either true or false. For example, a hypothesis A can mean that our measurements have a certain outcome. Note that the Bayesian sample space is richer than the frequentist one. Hypothesis A can also be of the type standard model is true or the Higgs boson is a composite particle. The Bayesian probability is our degree of belief that the hypothesis A is true. Obviously, it is different for different people. Therefore, it is sometimes referred to as a subjective or personal probability. Actually, The meaning of the Bayesian probability is very close to what people have in mind when talking about probability in general sense. It's the Bayesian framework within which you are allowed to ask and address questions like, what is the probability that I have a certain disease? As answer to this question, you naively expect any number between 0 and 1 to be allowed, and indeed, the Bayesian probability of the hypothesis I have the disease can be anything in that range. On the other hand, there is no frequentist probability related to the hypothesis because this type of hypothesis is not an outcome of any experiment. In the frequentist approach, you either have or don't have the disease, but nothing in between. Within the frequentist approach, only thing you can do is to construct a medical test, an experiment. Then you study how likely it is for the hypothesis that you have the disease to yield the result you actually obtained in your test. Unfortunately, there is no stronger statement that the frequentist framework can provide. On the other hand, within the Bayesian framework, you have some level of knowledge already before you undergo the test. The experiment yields some result, and you update your Bayesian probability in the light of the experiment. To do this, you use so-called Bayes' theorem, which gave the name to the whole Bayesian statistical framework. Let's have a look at the Bayes' theorem now. Let's consider two hypotheses, A and B. The Bayes' theorem states that the conditional probability for A being true while B is true can be calculated as P of A given B equals to P of B given A times P of A over P of B. The proof is very simple. We just need to recall the formula for the probability of a simultaneous occurrence of A and B expressed using conditional probabilities. Probability of A and B equals the probability of A given B times probability of B, but this also equals to probability of B given A times probability of A. By simple reshuffling of the left and right hand side of this equation, you get the Bayes' theorem. If A is a hypothesis that you have a certain disease, and B is an outcome of a medical test, then the Bayes' theorem gives a prescription how to update the probability that you have the disease in the light of the medical test result. Let's have a close look at the individual terms appearing in the Bayes' theorem. Probability of A is a degree of belief that you have the disease prior undergoing the test. It is called a prior probability, and it is typically a subject to long debates. It is not always clear what the prior probability is. In our example of the medical test, it can be, for instance, an occurrence of the disease in the whole population, which can be known prior we do any kind of test. Needless to say that probability of A has no meaning or just doesn't exist in the frequentist statistics. Probability of B given A is the probability that the test result B given the hypothesis A is true. This quantity has a good meaning and can be evaluated even in the frequentist framework, which is actually of great practical importance. Probability of A given B is the probability ascribed to the hypothesis A in the light of the result B. Therefore, it is often called a posterior probability. Probability of B is an unconditional probability of the result B. It can be evaluated sometimes, but it is more often considered just as a normalization constant. Let's stress once again that the prior P of A and posterior P of A given B are meaningless in the frequentist statistics, while probability of B given A is not. In practice, we often estimate probability of B given A using the frequentist approach, and then use it as an input to the Bayesian theorem. It is useful to show explicitly how the term P of B and the Bayesian theorem can be calculated. Let's write down the Bayesian formula again. From the basic properties of probability, we know that probability of A plus probability of not A must equals to 1, because A and not A are mutually exclusive events. From this follows that the same rule must apply also to the conditional probabilities. So probability of A given B plus probability of not A given B must be equal to 1. If we apply this identity to the right-hand side of the Bayesian formula, we see that sum over all possible values of A of the ratio P of B given A times P of A over P of B must equal to 1. Because the nominator of this ratio does not depend on A, the sum actually only applies to the numerator. From there, we can get an explicit formula for P of B. P of B equals to probability of B given A times probability of A plus probability of B given A, not A times probability of not A. So you can see that the denominator in the Bayesian formula can always be calculated as a normalization factor for the numerator, where we sum over all possible values of A. Let's take some concrete example, and we will see how important and natural the Bayesian statistics is. Actually, it is equally important branch of statistics as the frequentist one. For example, medicine builds a lot on the Bayesian statistics, and therefore the following example is from the field of medicine. Let's assume that there is a test for a disease with an efficiency of 100% and with the false positive rate of 1%. From some previous medical study, we know that the disease occurs in the population with a rate of 1 per mil. This can be measured, for instance, by counting patients where the disease has fully developed. What is the probability that you have the disease if the test came out positive? Let's write down the probabilities from the Bayesian theorem first. The test efficiency is the probability for the test to be positive given that you are ill. The test false positive rate is the probability for the test to be positive given that you are healthy. The prior probability that you have the disease before undergoing the test is typically the tricky part. However, In this example, it is quite natural to build on the known occurrence of the disease in the population, which is 1 per mil. The unconditional probability of a positive test result can be considered as a normalization factor for the numerator of the Bayesian formula, as we showed previously. It can be determined as a sum of two known conditional probabilities. Probability of the positive result equals to probability of positive result given you are ill times probability of you being ill plus probability of positive test result given you are healthy times probability that you are healthy. Here it is natural to set probability of you being healthy as a probability of not being ill, namely probability of being healthy equals to 1 minus probability of being ill, which equals to 0.999. If we put everything together, we get probability of being ill given the positive test result equals to a ratio of probability of positive test result given being ill times probability of being ill over probability of positive test result given being ill times probability of being ill plus probability of positive test result given being healthy times probability of being healthy which equals to 1 times 0.001 over 1 times 0.001 plus 0.01 times 0.999 which equals to 0.099%. Despite the test being efficient, the posterior probability is so low because our prior knowledge of the disease indicates that it is very rare. If we had no prior knowledge of the disease, then we can assume, for example, that prior probability of being ill is 50%. Then the posterior probability of being ill given the positive test result is 99%. From this example, we can see that Bayes' theorem is a very useful tool if it is used with reasonable priors. As an ultimate demonstration of this fact, let's try to calculate posterior probability in yet another way. Let's assume we have a group of 1,000 people. In this group, let's one person has the disease. Let's test all the people. Given the 1% false positive rate of our test and its 100% efficiency, we get 11 positive results. Therefore, being one out of the 11 positively tested people means that you have the disease with the probability of 1 over 11, which equals to 9%. This is exactly the result previously obtained with the Bayes' theorem.